Now today we're going to be talking about moisture in the air. So last week we talked about temperature, now we're going to begin talking about moisture. So this lecture in particular is going to be on latent heat and the water cycle, two very important concepts that are covered in moisture. And these are the pages that this lecture is based off of, a little bit from back in chapter 2 on latent heat, and then a little bit about the water cycle. So if you're ready, let's dive in. Now, a few of our goals for today are to, one, understand what latent heat is, how it's exchanged with the atmosphere during a phase change, to also understand what condensation, evaporation, and so on are, and then later in our future lectures for this module, we'll also be talking about relative humidity, dew point temperature, and so on. So, first thing I should mention before we even get started is right now you are in a room or somewhere surrounded by water. Believe it or not, you are surrounded by water. And the reason why you are is because in our atmosphere, there's a certain amount of water vapor. This leads to what's called humidity. And if you are like me, circa 2006, when I was in college, you probably had a lot of bad hair days due to humidity. In case you're wondering, no, I've cut my hair. It doesn't look nearly that silly now. But yeah, if you've ever had a bad hair day and wondered why, big part of it has to do with humidity. So let's begin by talking about why humidity makes days, hot days in particular, so incredibly miserable. It all has to do with what's called latent heat. Now, our Earth is unique. It's the only planet in the solar system where water is readily available in all three phases. It's the only planet in the entire solar system where this is true. If you are on Venus or on Mercury, if there is any water, it's so hot that it's in the vapor stage. If you're on Mars or on Saturn or on Jupiter or further out, there's no real water vapor. In those cases, it's so cold that there might be slight amounts of liquid water, but for the most part, it's really ice. Whereas here on Earth, we have water readily available abundantly in all three phases. And these three phases are solid, ice, snow, and so on. Liquid, water drops, rain, clouds, you all see liquid water in everyday life. And then gases, water vapor, and humidity. Now, with this said, water doesn't like to hang around in any one phase. Rather, water is constantly changing between gas and liquid, liquid and gas, liquid and solid, and so on. We call these phase changes. Phase changes. And water undergoes a phase change when it transitions, when it transforms from one phase, either liquid or gas, to another phase, solid or so on. Now there are several well-known phase changes that I'm sure you've all heard of. There's evaporation, which is the process of going from liquid over here to gas over here. Then the reverse can happen where you go from gas to liquid. That's called condensation. And then going from liquid to solid is called freezing. From solid to liquid is called melting, and so on. So I'm sure you've already heard about all of those. But what you probably haven't heard about yet is something really interesting happens when water changes phases. And that something really interesting is called latent heat. So here's how latent heat works. In order for water to maintain its phase, it has to hold a certain amount of heat in its bonds. So those are the bonds between hydrogens and oxygens. And these bonds And this heat in between these bonds is hidden heat. And the reason why it's called hidden heat is because it does not affect the temperature of the water. Instead, it solely affects the phase of the water. Now, when water undergoes a phase change, it either absorbs more heat into those bonds or it releases heat from those bonds, depending on the phase change that it undergoes. Now, what's interesting about this is as water is undergoing a phase change, it can be absorbing or releasing heat with no change in temperature. Don't believe me? Well, there's an easy experiment that you can do. Pull out a glass of ice water, get a thermometer, stick it in there, make sure that there's plenty of ice in the glass, and hang out there. It'll take a couple hours. I know, kind of boring, but it'll take a couple of hours. But what you can actually do is every few minutes stir up that ice water and measure the temperature. And what you'll notice is as long as there's ice in that water, the temperature doesn't really change much. It might warm a degree or cool a degree depending on where in the water you're sticking the thermometer. But the fact of the matter is, as water is melting, any heat that's being absorbed by that water isn't going towards raising the temperature. Rather, it's going towards melting the water. And so, essentially, as ice heats up, its temperature rises until it reaches the melting point. Once it reaches the melting point, it levels off as the ice is melting. And any new heat being absorbed goes to simply changing the phase rather than warming the water up. Now, once all the ice has melted, the water will begin to warm again. The water will begin to warm again until it reaches the boiling point. The boiling point is 100 degrees Celsius. Once it reaches that point, temperature again will level off until all of that water has evaporated. And then it'll continue to warm up again. So if you don't want to do the first experiment and bore yourself for 3 hours, the other experiment that you could do is boil a pot of water. As you're boiling the water, as you're heating it up, watch the temperature increase. Once it reaches 100 degrees Celsius and begins to boil, watch what happens. Even though you're continuously adding heat to the pot, the water is not increasing in temperature. And the reason why is, again, because all the heat that's being added to that water is going towards evaporating the water. It's going towards evaporating the water. So all of that said, the way latent heat works is when water melts or evaporates, we call that moving up a phase. Whenever water moves up a phase, it absorbs heat from its surroundings. And that heat goes to simply change its phase. On the other hand, when the reverse happens, when water vapor condenses back into liquid, it releases that heat back into the surroundings. That's going to be very, very important in our next module when we start talking about stability. It's going to become very important. And then the same thing when water freezes, as it goes from liquid to solid, it releases heat. Now, this is what's confusing about this. So just a quick review before I get into that. Whenever you move up a phase, the water absorbs heat, causing it to change its phase. Whenever water moves down a phase, it releases heat. It releases heat. And that's what allows it to move down a phase. Now, the confusing part about this is when you and I think about what a heating process is, what a cooling process is, and so on, we're probably thinking about what's happening to the water. But the fact of the matter is, in terms of meteorology, we don't care about what's happening with the water. We care about what's happening with the atmosphere. And so when water condenses, when it goes from vapor to liquid, it actually releases heat, warming the atmosphere up. On the other hand, when water evaporates, when it goes from liquid to gas, it actually absorbs heat from its surroundings, cooling them down. This is one of the reasons why we sweat. If you've ever wondered when it's hot outside, your body starts to sweat, it's because the atmosphere actually let me rephrase that. The reason why your body sweats is because when the atmosphere is hot, it forces that sweat to evaporate. As that sweat evaporates, it sucks in heat from its surroundings, cooling the surroundings down. That's how sweat cools our body, because all those little beads of water on our body are being evaporated, and by evaporating, they're sucking in latent heat, cooling the air around down. Now, this is also why humid days are so bad, because when it's humid outside, water can't evaporate easily, and so your body can't cool down. Also, there's a lot of condensation happening on humid days. This actually causes heat to be released, making it feel warmer than it otherwise is. So, with all of that said, when you go from ice to liquid or from liquid to vapor, you're actually absorbing heat. Water is actually absorbing heat from the surrounding atmosphere, cooling the atmosphere down. On the other hand, when you move down phases, when you go down from vapor to liquid or from liquid to ice, that actually releases heat into the atmosphere, warming the atmosphere up. Now, there's two other phase changes on this image that I should talk about quickly. Sometimes ice actually skips the middleman, and instead of melting and then evaporating, ice actually skips that and goes straight to evaporation. The opposite happens too, where water vapor will actually go the opposite way from vapor back to ice. Now, these two processes are called sublimation, going from ice to vapor, and deposition, going from vapor to ice. Now, going from ice to vapor is again moving up a phase. Therefore, in order for it to happen, it has to suck in heat from its surroundings, cooling those surroundings around. Cooling those surroundings down, and therefore making them not as hot as they were. On the other hand, when you go down a phase from vapor to ice, that actually releases heat into the atmosphere, warming it up. Now, this is a confusing topic, and the reason why it's so confusing is because, again, you're thinking, and I'm thinking, when I say warming process, cooling process, and so on, it's easy to think, well, isn't the water warming? When evaporation occurs, isn't the water warming up? Or when it's condensing, isn't it cooling down? Well, I say to you, yes, it is. But we don't actually care about what's happening to the water. We care about what's happening to the atmosphere. When water evaporates, it takes heat away from the atmosphere, cooling the atmosphere down. So even though the water is warming up, the atmosphere is actually cooling down in the case of evaporation. And then in the case of condensation, even though the atmosphere, or even though the water is cooling down, it's releasing heat into the atmosphere, warming the atmosphere up. So it takes a little bit of practice, and you'll probably have to go over this a couple of times. Be patient about it, take your time with it. It's a tough concept, But again, whenever water moves up a phase, that cools the atmosphere. Whenever water moves down a phase, that warms up the atmosphere. Now, why do we care about this? Why even talk about this? Well, the reason why is because this latent heat that's stored in the water actually ends up being hidden energy. It ends up being hidden energy. So when water evaporates near the surface, as it rises into the atmosphere, that actually allows that heat to then be released when the water condenses. This allows for thunderstorms to grow taller. This allows hurricanes to intensify. This allows storms to become stronger. It's this latent heat that actually acts as fuel for the atmosphere. And if we didn't have latent heat, our atmosphere would be so much more boring. So much more boring, because that latent heat allows air to continue to rise. Simply because as it rises, it condenses. That releases the latent heat, allowing the air to continue to rise. Another good example of this is hurricanes. So this is Hurricane Katrina right here, one of the most infamous hurricanes in world history, especially here in the United States. Well, hurricanes feed off of extremely warm ocean waters. And the reason why they do is because as those warm waters rise, they have a lot of latent heat that they release feeding into the storm. Well, in the case of Katrina, it underwent a process called rapid intensification right around here, where it quickly jumped from a minor Category 3 hurricane, or from a weak Category 3 hurricane, to an intense Category 5 hurricane. And Category 5 represents the strongest hurricane possible. And so this hurricane exploded in intensity. Well, in order for it to do that, it had to absorb a lot of heat and a lot of moisture. Well, it was standing over a pool of really warm water. And it basically sucked up that water. It evaporated that water into its system the same way you would suck water out of a cup using a straw. What was left behind was actually cooler water. And so these little areas where there's suddenly a cooler patch in the ocean occur simply because as a hurricane intensifies, it sucks up all that warm water. Well, that's what happened here. As Katrina passed over this area, it sucked up a lot of heat and a lot of moisture out of the water here, causing it to explode in intensity. If there was no latent heat in that water being released into the storm wouldn't have grown as intense as it did. Now, the last thing I'm going to talk about in today's lecture before we move on into saturation and so on is what's called the water cycle. Now, I'm sure you've all heard of the water cycle at some point in your life, so I'm not going to bore you to death with it. But I do want to at least give you a quick rundown of it, and I call this the TLDR version. I have the text on the next slide, but since I have this slide up, I'm just going to follow with this slide, and then I'll show you the text on the next slide. So here's how it works. On a sunny day, ocean water becomes really warm. As the ocean becomes really warm, the water on the very top of the ocean can become much hotter. This allows that ocean water to rise. As it rises in the atmosphere, it does what you learned in the last module. It expands and it cools. Now, as it cools, that water condenses, forming into clouds. Now, eventually what will happen is wind will carry these clouds over land. And as it's carried over land, it rains out or falls as snow or some kind of what's called precipitation. This precipitation then hits land, either in the mountains or down near the coastline. And this water, this precipitation, then runs back down to the ocean and back into the ocean. And the cycle begins again. So, water heated by the sun evaporates, rises, condenses into clouds, is then carried over onto land by the wind, where it rains out, and then back down. Now there's other steps in this cycle. Some of this water can be absorbed into the ground, some of it can be channeled into lakes, some of it can freeze into glaciers, some of it gets absorbed by plants and then transpired, basically sweated out of those plants, back out into the atmosphere. And this is just a handful of possible scenarios. What I want you to focus on, though, are just the main steps. So, ocean heated by the sun, water evaporating into the atmosphere. As that water rises, the air in it expands and cools, causing it to condense. Then wind blows the clouds over land, where they precipitate out. The precipitation then runs back down into either lakes or rivers or back out into the ocean, starting the cycle all over again. That's what I want you to focus on. Don't worry about transpiration, don't worry about glaciers, don't worry about runoff. Focus on just these main steps of the water cycle. Now, that's it for today's lecture, but do me a favor before you begin the next lecture. Go get yourself a glass of water or some kind of soda or something liquid. Bring it back to you. Feel free to enjoy it, but also hold on to it for the next lecture. Until then, I'm Terrence Mullins. You've been good. Thank you so much.